When you analyze any of these schemes, you care about the threshold, you care about how much noise it can tolerate. You also care about the overhead. And people have studied this, and there's lots of good papers that study it. Here's just one example. So these guys looked at Shor's algorithm for 1024-bit number. And here, they're counting the number of gates used in the circuit, the number of gates used, and the number of different gates used. So this is 14% of the gates, or 10 to the 9 gates, which is 14% of the total. Sorry? I don't know. Are C0 gates. Some of them are Hadamard gates, and some of them are T gates. But then when you encode it, but then when you encode it onto an error correcting code, the gates that you use changes quite a lot. So for example, if we're using like the 913 Bacon shortcode or the 2515 Bacon shortcode, actually most of the work is swapping qubits around the two-dimensional lattice, because you got to move them around to talk to each other. So this has changed completely into this. You have a lot of C0 gates for error correction still, even more C0 gates for error correction. Whereas if you use a different code like the service code, no longer do I have swaps, but now I just have even more C0 gates. So that's kind of fun to see how things change. You can also see tables like this. Which of these is most interesting? So you can just go over these figures forever, I suppose. So here what they've done is, let's ignore this table, this column. So these two columns compare superconducting qubits with ion traps at supposed error rates. So they're assuming that the error rate on superconducting qubits gets down to 10⁻⁵, which is 2 or 3 orders of magnitude lower than it is in today's devices. And they assume that the error rate on ion traps goes down to 10⁻⁹, which is, substantially lower than error rate in today's devices, like 6 orders of magnitude lower or something. But I mean, so ion traps are really good. So it is possible that you can get the error rate much lower than in superconducting qubit, potentially. And then what they do is, for each of these models, they try different codes. So they try the surface code and they try the Bacon-Shor code. These are some of the most promising, two of the most promising error correcting codes. And then they show, for example, that the surface code, these are the numbers they get to do factoring Shor's algorithm. So it takes 11 hours versus 2 years. Here it's 5 years versus 58 days with the Bacon-Shor code. And so, depending on what your error rate is, 10⁻⁵ versus 10⁻⁹, very fast gates versus very slow gates, it'll change which code you want to use. That's one simple conclusion from this. But they also count things like the number of physical qubits that you need in order to do this. So 10 to the 7, 10 to the 8, 10 to the 12, 10 to the 5. Right, so the Bacon-Shor code it's not looking good for superconducting qubits. Yeah.
Don't you need more qubits for higher error rates?
What is there a contradiction, or what do you?
For the superconducting qubits.
Yeah.
Number of qubits is 10⁻⁷ at higher error rates and 10⁻12 for lower error rates.
You're saying this versus this?
No.
This versus this?
Yes.
Oh no, so the error rate's the same. These are both the same error rate. It's just the code is different. So we're changing the Fontana scheme. Yeah, so I think, so what's got to happen here is, the reason this number is so large, it must be that they had to take I think it's a distance 5 Bacon-Shor code, did it say? I think they take basically you're going to need like 2 or 3 levels of concatenation here, and each level of concatenation blows you up by a factor of 25. That's got to be what's happening. So actually, like, even a slight change in the error rate, if it means you need a whole other level of concatenation, it's going to blow up your overhead, even though the error rate has changed just a small amount. That's probably Yeah, and like this number here, so for example, here versus here, like, why is it backwards? 10 to the 5 versus 10 to the 8. I mean, basically, the Bacon shortcut is, it's just a more efficient code, I guess, so the surface code is not that efficient. And this is often the case, is that more efficient codes are better, very low error rates, than high error rates, because they just have sort of an initialization cost that you have to get over. Okay. I don't know. So sorry, I could talk about that forever. Let's not. Let me. I wanted to get to this today, so let me try to get to it. Let me explain the surface code. We only have a couple minutes, but I think that's enough time to explain the surface code. Give you some intuition for it at least.